Hello everyone. In this presentation we are going to understand the significance of transforms in real-time application. We are all familiar with the amplitude modulated signal. You are able to see this is the amplitude modulated signal where the amplitude of the carrier is varied with respect to the amplitude of the modulating signal. This is well known. And if you take a transform for this amplitude modulated signal, already we have seen the waveforms like this, and this is the cutoff frequency, and that is the upper sideband, and this is the lower sideband. So this is the common amplitude modulated signal all of us are familiar with. When you relate this with signal processing, it's very interesting. So if you look at this particular signal, so there is a cutoff frequency which looks like one impulse, and the upper sideband is looking like an impulse, and the lower sideband is looking like an impulse, and these three impulses can be called as discrete time signal. So a discrete time signal in the frequency domain, when it transforms to, or when you take an inverse transform to the time domain, it becomes continuous and periodic. It's very interesting. It becomes continuous and periodic. So as we discussed already, as being discussed in the digital signal processing, discreteness in one domain gives continuous and periodicity in other domain. So if there is a discreteness in time domain, in the frequency domain we will get continuous and periodicity that you see here. So here, this is the, let us say this is the DC signal. Let us say this is the DC signal, which is a 5-volt signal, and when you take some samples here, you will get a samples like this. This discreteness gives, if you take a transform for this discrete samples, you will get continuous and periodic. So when you get continuous and periodic means what? Periodic means what? You can keep on repeating the same. That is why periodic. So the analyzing the periodic signal means analyzing one period is more than enough to analyze all the periodic signal. So that is the understanding here. Okay. So coming to this DC signal as discussed right now, there is a 5-volt DC signal, and if you are going to take 8 sample means it is beginning 8 samples. All the 8 samples are unique. Let us say it is 5 volts. When you take a transform, or when you take a transform for this 5 discrete time signals, you will get the frequency term. What is the frequency term? Frequency term is 0. DC signal have no frequency. DC signal have no frequency. Hence, if you take a transform for the DC signal, you will get an impulse in the frequency domain. So this is the impulse in the frequency domain. So this is the frequency axis. Because the DC signal have no frequency, so there is no frequency components available. There is only DC component available. So capital X of 0 is a DC component. So here there are 8 samples. So 8 amplitudes, that is 8 5 volts, where 1 1 1 1 1 1 1 1, assuming 1 1 1 1 1 1 1 1 means all are DC. So the amplitudes are DC signals, hence the gain of the DC signal is 8. So 1 1 1 1 1 1 1 1, when you take a transform, we are getting 8 followed by 7 zeros. That means there is no frequency component, only there is a DC component. So DC components are added, the gain is more. So that is what we need to understand. So if we are talking in terms of storage, storing the 8 values, 8 samples is complex when compared to storing only one value. So here in the time domain, if you are storing this signal means you need 8 locations. But in the frequency domain, to store this value, we need only one location. So 8 times we are able to reduce the storage space. So from this discussion, it is very clear that instead of storing the signal in time domain, it is better to store the signal in the frequency domain, which occupies very less space. So always transforms are helpful in compression. It is very interesting. Transforms are helpful for us to do compression. So because compression is mandatory, so always all the videos and the audios are compressed signal. Video, audio and images all are compressed. Video, MPEG videos are compressed signal. JPEG images are compressed signal. MP3 is also compressed audio signal. So the compression is happening in the transforms similar to this. So expansion in one domain gives compression in another domain. That is how it works. Okay. So as we all know, there is something like f of t. We have studied f of t. So that is decimation in time fast Fourier transform. Already we come across decimation in time fast Fourier transform. How to take a transform? We know this. The expression for finding out the transform is x of k. X of k equal to sum of 0 to n minus 1. Sum of 0 to n minus 1 x of n into e power minus j omega n. This is what the formula for finding out the transform. So here if we see here x of n, when we are taking samples, something like this, when you are taking samples, time domain means it is discreteness and the frequency domain means it is continuous, that you can able to see it very clearly. X of n into e power minus j omega n, where minus 2 pi f. So omega means 2 pi f is the frequency, 2 pi f. So this f is continuous, this n is discrete, this n is discrete, this f is continuous. Because it is continuous, so in the frequency domain you will get a frequency like this. This is continuous and periodic in other domain means it is something like this. This is f. This continuous signal cannot be processed by digital computers, because when computers are computing means the value should be finite. So this continuous f, we are going to take the samples. How many samples? K samples. Okay, so this f is discontinuous and we are going to take a samples, k samples. So the samples are 1, 2, 3, 4, 5, 6, 7, 8. We are going to take 8 samples in this continuous periodic frequency in the frequency domain. So when you take samples, this will become x of 0, x of 1, x of 2, 3, 4, 5, 6, 7, this is k. So when you take sample, time domain also we have a discrete signal. In frequency domain also we have discrete signal. So both in time domain and frequency domain the signals are discrete, hence it is computable by a digital programmable device like microprocessors and microcontrollers. Because in both the domains we have made it as discrete, so it is countable. If it is countable, you can able to compute. So that is what the formula here. So this is what the f of t. So taking the sample in the frequency domain, k samples out of n, kth sample out of n. So if you are taking e power minus j 2 pi by n means this is called as Twiddle factor for f of t. This is called as Twiddle factor for f of t. And very interesting thing in this periodic signal, as you see, very interesting thing in this periodic signal means, so instead of finding out x of 0 and x of 4, find out x of 0 and change the sign. Changing the sign alone can able to help us to identify the same signal. That is what the butterfly diagram says. In the decimation in time fast Fourier transform, we used to put a butterfly diagram. The significance of this butterfly diagram is reducing the computational complexity. How it reduces the computational complexity means, in the periodic signal, if we say x of 0, if we are finding out x of 0 means the x of 4 signal is similar to x of 0, with change in sign. Similarly, x of 2 is similar to x of 6 just by changing the sign. That is why x of 0 and x of 4 by changing the sign, x of 2 and x of 6 changing the sign, and x of 1, x of 5, x of 3 and x of 7. This we call it as bit reversed order. And the significance of butterfly diagram, significance of transform, something like sampling in one domain gives continuous and periodicity in other domain from the amplitude modulated signal. And the significance of f of t means in both the time domain as well as in frequency domain we are able to get a discrete signals, hence it is computable, and dit f of t alone can be computable by digital programmable devices or digital signal processors. That is what we are going to see in an experiment here now. So here if you see 1 1 1 1 1 1 1 1 is the input, means 8 followed by 7 zeros are the output. 1 1 1 1 1 1 1 is the input, means 8 followed by 7 zeros is the output, as we discussed now. So here we have a kit. Texas Instruments Tiva development board, which has Tiva microcontroller here, which is TM4C123GH6PM. This Tiva microcontroller have ARM CORTEX-M4, which has DSP features, which is capable of performing signal processing operations. In this demo, we are able to see how the ARM CORTEX-M4 based Tiva microcontroller from Texas Instruments is going to do DFT. Here, this is Tiva launchpad, which is connected to the laptop, where the IDE what we are using here is Energia IDE. IDE what we are using here is Energia IDE. And after installing the necessary header files, with respect to FFT means, as we see here, so that is an Arduino FFT. So we are going to introduce the first header file. We are going to include the first header file, Arduino FFT.h, and we are going to use 8 samples. As per the discussion, we are going to use 8 samples, and all those 8 samples are 11111111. That is what which is available in a float variable, something like 11111111. And we are having the another inbuilt function is Arduino FFT of Arduino FFT function, and then we are using the real number and imaginary numbers in the output. So for real number we are having 8 samples, for the image number we are having 8 samples, and we are interested to find out FFT for the signal. We are interested to find out FFT for the 8 samples. For that we are using the for loop. For 8 samples. Number of samples is 8. Here we are getting real value as well as the imaginary value. Here we are able to storing the real value x of 0, x of 1, x of 2, x of 3, x of 4. So real values are stored, imaginary values are made 0, and all the values are kept in the V real and V imaginary. 8 values are kept in the real and imaginary, as we see here. And this is very important thing. As we compute the FFT in the MATLAB, here with respect to Energia, there is a convenience here. FFT of, there is a possibility for us to find out the FFT by using this command, FFT compute with real value, imaginary value and samples FFT forward. That is, we are finding the transform. And after finding the transform, the real value and imaginary values are stored in the corresponding real and imaginary variables, and then we are going to plot those values. We are going to plot those values by using the for loop, real value separately and the imaginary value separately by separating with the comma, as you see here. So this is the simple code, and we are going to execute only once. The input samples are 11111111, and we are expecting 8 followed by 7 zeros, as we normally do in our conventional DSP. So let me download this code. Now I am downloading this code. It is getting downloaded in the ARM CORTEX-M4 based Tiva microcontroller here. And once if you have downloaded, it is ready to work. And now because we are using the serial window, because we are printing everything in the serial print, let me look at the serial window here now. So the serial window is available here. So now I am resetting this kit. Means it will execute only once. Now I am resetting this kit. If I am resetting this kit means it is execute only once. And if you see the screen, you are able to see 8.00 and 0.00. What is this 8.00? This is the real number, imaginary number. This is capital X of 0. X of 0, X of 1, X of 2, X of 3, X of 4, X of 5, X of 6 and X of 7. So X of 0, which is there is a no frequency component, which is DC component. Because the input is a DC signal which is 5 volts, as we know very well. The input is a DC signal as 5 volt, as we see here. This is the 5 volt. We are taking 1, 2, 3, 4, 5, 6, 7, 8 samples. So 1, 1, 1, 1, 1, 1, 1, 1 are the sample. And if you take a transform, the DC term is available at the 0 frequency, which is 8, and followed by 7 zeros, which is the discrete Fourier transform output. That is what we are able to see here. 8 followed by 7 zeros in the real term, and obviously there is no frequency means there is no frequency term. So once again I am running this. I am just clearing the screen. I am just clearing the screen, and then I am resetting. This means it is executing once. And then we are able to see the corresponding value 8 followed by 7 zeros as we see here. Now the fast Fourier transform is implemented in the ARM Cortex-M4 based Tiva microcontroller in Tiva launchpad in the real time. This is very interesting. Similarly, we can able to perform the inverse FFT. The FFT and inverse FFT, all transforms are invertible. As we know, all transforms are invertible. The formula for inverse FFT is x of n. So we are interested in getting time domain signal which is x of n by using the frequency domain signal x of k. So x of n equal to 1 by n into sum of k equal to 0 to n minus 1 into capital X of k into wn power minus nk. Only change is wn power nk in the trivial factor. We are changing the sign alone in the inverse transform, and here you are introducing another term called 1 by n. So this is inverse fast Fourier transform, this is forward fast Fourier transform. Only difference is change in sign and 1 by n. It's very easy for algorithm to compute and etc. That is what we are able to see. Once again, if we are going to the inverse FFT, the same code which is written in some other way. So again 8 samples as we discussed right now. 1 1 1 1 1 1 1 1 is the input, means the transformed output is 8 followed by 7 zeros. That is given as an input now, and these are all the examples in the frequency domain, and we are able to get this y samples in the time domain. So Arduino FFT, the same function, and we are using the same variable of real sample and imaginary samples. Means there are 8 samples. So real 8 variables and imaginary 8 variables. These are double variable, and here we are putting our for loop here. To fill the values 8 followed by 7 zeros in the real term, and the imaginary terms also filled by the corresponding zeros as we see here. These values are filled in the corresponding real and imaginary, and then we are computing the FFT, inverse FFT. We are computing the inverse FFT as we see here. It's very interesting. We are computing the inverse FFT. If you see here, only difference is FFT compute, V real, V imaginary, and samples all are same. Only change in the code is FFT underscore reverse. In the earlier case, we have done a code called FFT forward. So if you put a reverse, means it is inverse FFT. So that is the more convenient in the Energia tool, and that is the more convenience in the Arduino header files. So this is happening just because of Arduino FFT.h header file is more comfortable for us. So something like how do we develop in the MATLAB, we can able to implement in the hardware also. And then if you run this code, now I am downloading this code into the kit. So the program is getting downloaded. After downloading, we are interested to see the results in the serial window. Now we are able to see the result in the serial window. We are able to get the output continuously. We are able to see that we are able to get the values 1 1 1 1 1 1 1 1 1 1 continuously. If I am stopping this, means it has stopped, right? It has stopped, and I can clear this, clear the window. I can clear the window as we see here. I can clear the window. When I release this, means it is continuously giving the values 1. So instead of doing the fast Fourier transform and inverse fast Fourier transform in MATLAB, the FFT and IFFT is being experimented in the ARM Cortex-M4 based Tiva microcontroller with the help of Energia tool here. It's very interesting to learn FFT transforms and inverse transform with Energia and Tiva microcontroller. Fortunate. Thank you very much.